Okay, so as we look at these factoring warm-up problems, you should have noticed that they were all the same type of problem. Number one, what did we end up with? X minus 2 and x minus 2, or since it was the same factor twice, we can write it as x minus 2 squared. The second one, what did we get? X plus 5 squared. Oh, so both of the problems so far ended up becoming perfect squares. What about number 3? X minus 9 squared. Oh, another one that's a perfect square. Number 4, I gave a leading coefficient where the other ones didn't, but we should first factor out that 2 because I could divide everything by the 2. So factor the 2 out of everything. The 2 stays out there, but when I factor x squared minus 2x plus 1, that becomes x minus 1 squared. So each one of those became a perfect square, and that's important to what we're going to be doing today. So I want to make a couple of generalizations or observations about the type of problems that became perfect squares, because that's our goal, is to have perfect squares today. So pay specific attention to the B and the C and their connection to the number we put into the factor. So on number 1, and I don't know that number 1 is the best one to look at initially because both B and C have a 4, and then maybe look at a different one first. Look at number 2, we have a B value of 10, a C value of 25, and we ended up with a 5 in our factor. What observations can we make? They're both divisible by the 5. Both B and C are divisible by 5. That's true. Pay also attention to number 3, where B is negative 18 and C is 81, and we ended up with a negative 9 in the parentheses. There, negative 18 and 81 are also divisible by the 9, but hopefully we start to see more of a pattern than just that. How does the B compare to the number that ended up in the parentheses? B is double the number that ended up in the parentheses. Negative 18 was twice as large as negative 9. How does the C compare to the number that was in the parentheses? It was squared. So in each one of these cases, that C value was actually the B value cut in half and squared. That was the relationship that existed in the C spot. We took the negative 4, cut it in half to get negative 2, and we squared it, we got 4. Half of 10 is 5, squared is 25. Half of negative 18 is negative 9, squared is 81. Down here, after I factored out the 2, I would take half of negative 2, square it. Half of negative 2 is negative 1, square it, you get positive 1. And so the number that went in the parentheses was just the B over 2, half of B before you square. It's an important thing to notice as we get into section 4.5, which is where we're going to go right now. So 4.5 is titled Completing the Square. And our goal or our target for today is that we will add another tool to our repertoire of how to solve quadratic equations. So specifically, we could say our goal after today is that you would be able to complete this, solve a quadratic equation by completing the square. So that's what I want you to be able to do. I want us to start off the solving problem. I'm going to be pretty strategic about the problem I give us. X squared minus 16, we'll call this problem number 1. X squared minus 16x plus 64 is equal to 49. The format of the problem is different than the formats we used in the previous solving problems. Because what do we observe? What's different here? It's not equal to 0. When we were factoring or when we were graphing, we wanted it set equal to 0. I don't want it equal to 0 when I'm completing the square. Instead, my hope is that the left side, or it could have been the right side, but I'll usually go with the left side, is a perfect square. Does this follow the same pattern as the problems we just did for warm-up? Will it become a perfect square? And when I factor it, yeah, because half of b is -8. That's what should go in the parentheses. And when I square -8, I get 64. Yes, it does, in fact, factor to x minus 8 times x minus 8. So the goal was that one side was a perfect square. I didn't care about the other side. Probably isn't going to be a 0. And then I want to solve this. How can we solve this? What we did in the last unit, we practiced a little bit to get rid of a square. I would square root. And when we square root, we have to remember the plus or minus. When I introduce a square root to solve a quadratic equation, you can't forget the plus minus. If you forget it, you're losing one of your answers. So now I have x minus 8 on the left side, plus minus 7, because the square root of 49 is 7. I'm trying to get x by itself, so I'm going to have to add 8, but notice there's two things on the right side. There's a -7 and a +7. So we may want to break it apart into two equations. So when x minus 8 is equal to 7, you'd add 8 to both sides to get 15. Over here, you add 8 to both sides, and you get 1. Please don't make a mistake that I see often. I'm going to put it in red because it's wrong. Here's what I see sometimes. At this point, add the 8, say it's x equals plus minus, well, 7 plus 8 is 15. And there's my answers. I did get one of the answers, but one of them is wrong. So don't just add the 8 to the 7, because in one case it was 7, in one case it was supposed to be a -7, and then it's the wrong answer. So please don't make that mistake. Okay, let's take a look at another problem. When I look at this second problem, I notice that it is set equal to 0. And is this a problem that is factorable? Absolutely it is. X minus 1, x minus 15. Honestly, if I were to have been given this problem, I probably would have solved it by a factoring. But as you'll see in a little bit, some problems are not factorable. So factoring is good when it works, but it doesn't always work. That's why we have to have other strategies. So yes, I would probably use factoring for this problem, but that's beside the point. We're going to talk about how to do it by completing the square. What I want you to observe is contrast this with the last problem I just did. I did x squared minus 16x plus 64 equals 49. Here I have x squared minus 16x plus 15 equals 0. Aren't they the exact same problem? This is the exact same problem as number 1. This is the exact same problem as number 1. It's written slightly different because I have it set equal to 0. But if I would have taken number 1 and set it equal to 0, wouldn't it have looked like this? Yes, and if we were going to factor, I'd want it in this form. We are not factoring. I don't want it in this form. So what should I do if I were going to complete the square? The section is called completing the square because I want to make sure that the number in that constant position, the C value, is the correct number. Is that the number I want in the C spot? It's not. So what I'm going to do, and I know I've already solved this problem, I already know what the answer is going to be, but we would move that 15 over. I don't want it set equal to 0. I actually want to move the 15 out of the way and leave a spot for the number that I want. What number do I want in that position? 64. We don't know it just because it was problem 1, but we know that because of our warm-ups. Remember, whatever our B was, we wanted to cut it in half and square it, and that's what should go in the C position. So if our B is negative 16, half of negative 16 is negative 8, but negative 8 squared is positive 64. I want a 64 right there. But is it okay to just go and add 64? It is okay as long as I do it to both sides. So if you add a 64 on the left, you're going to have to add a 64 on the right. What do I have on the right side now? Oh, 49, kind of like I did on number 1. No, what is the left side factor to? X minus 8 squared. Oh, kind of like the last problem. So to finish this problem, I'm going to go through the rest of this problem quickly because we already did it on the last problem. I don't think we need to spend a lot of time finishing this one, but don't forget to do your plus minus when you square root. I'm going to add 8 to both sides, but be careful on the right side. Remember, we're adding 8 to a positive 7, and we're adding 8 to a negative 7. Don't just call it a 15. 8 plus 7 is 15, but then 8 and a negative 7 together make 1. Oops. So 15 and 1 are still my answers. Take a look at another one. Look at the C position. I have a 9. Is 9 the number that I want? No. Could I factor this one? I could factor. I could find my answers easily and more easily by factoring than what I will do on completing the square. Once again, that's beside the point. There will be cases where we can't factor, and that's why it necessitates other methods. But let's go ahead and show you how to do this problem. This is an easy one. That's why I'm choosing to stick with it. We'll get into some that aren't as easy and we can't use factoring. Question? So the question was, how did I come up with using the number 64 in the last problem? That goes back to our warm-up problems where we observed that the number in that C position, use this formula right there. It was whatever half of B was and then squared. So when I came back over here to that problem and my B value was a negative 16, I really took the negative 16, I cut it in half, and then I squared it. So that gave us negative 8 squared is 64. That's how I knew 64 went there. So question number 3, is 9 the number I want in that C position? No, so I subtract it over to make room for the number I do want. So to figure out that number, the same question that was just asked, take the B value, which we know is 10, cut it in half, and then square that. Well, half of 10 is 5. 5 squared is 25. So I want to have a 25 there. That means I have to add it to both sides. Oops. Our left side should factor to a perfect square. Our right side conveniently, again, is a perfect square. It's not always going to be the case, but it is here. So now we square root, plus minus. So we have x plus 5 is equal to a positive 4, and x plus 5 is equal to a negative 4. I will be subtracting 5. So start with the positive 4. Take a positive 4 and subtract 5, you get negative 1. Then we have negative 4. Negative 4 minus 5 is a negative 9. Take a look at this problem. X squared plus 4x plus 11 equals 0. Can I solve this by factoring? Are there two numbers which multiply to 11 then add to 4? No, there are not. So this one cannot be solved by factoring. Could we have potentially solved it by graphing? Maybe. Can we solve it with completing the square? Absolutely. Completing the square always works. Factoring doesn't always work. Graphing doesn't always work. Well, I'll show you why in just a little bit, why graphing would not have worked for this problem. So, completing the square. I don't want 11 in the C position, so I subtract it away. It's a negative 11 on the other side. What number should I put in the C position? You take the B value and you cut it in half, and you square that. Half of 4 is 2, 2 squared is 4. We want a 4 in that C position. Negative 11 plus 4 is negative 7. Notice we do not have a perfect square on the right side this time, which means we're not going to have a very nice answer. But you might also notice not only is it not a perfect square, it's also negative. I wonder why we learned yesterday or Monday's section before we learned this one. Probably for reasons like this type of problem. We square root x plus 2 is equal to plus minus square root of negative 7. So we would break, let's think back to yesterday, or Monday rather. Square root of negative 7, you can break the negative 1 apart from the 7. Think about those two parts separately. What is square root of negative 1? I. What about square root of 7? Can I simplify that? 7 is prime. There is no factor of 7 other than 1 that is a perfect square. I cannot simplify that down. So it becomes I square root of 7. X plus 2 equals plus minus I square root of 7. So now to finish this, I have to subtract 2. We're not going to be able to simplify it with that I squared of 7. So it becomes very important that we put that negative 2, that 2 we're subtracting, in front of the plus minus. That way we're subtracting the 2 from the positive and from the negative. If we don't put it at the beginning, it does not get understood that way. So it has to go first before the plus minus. So negative 2 plus minus I squared of 7. I cannot simplify that any further. So those are the answers. One of them is -2 plus I squared of 7. The other answer is -2 minus I squared of 7. So you can see why it wasn't factorable. Those were not nice answers. But we should also be able, this also tells me why we could not have solved this by graphing. This is a type of problem. I don't know exactly what the graph would look like, but I do know that this is the type of picture that never touched the x-axis. We can have parabolas that don't touch the x-axis, and at that time, we would have said there were no solutions, but more precisely, we would have said there were no real solutions. Or no real roots. It doesn't mean there were no answers. It just meant they weren't real numbers. Instead, they were imaginary numbers like we just discovered. Our graphs, when we graph on an XY coordinate plane, we are only graphing real numbers. So imaginary numbers do not show up. There are graphs. There are ways to graph complex numbers, but it's a whole different graphing system, and we don't get into it in this course. So they can be graphed, but not in this course. It's basically adding another dimension to it. No, it's different than that. Just a complex graph. Let's try another one. Oh, I don't want to do this one yet. I want to do this one. Looks fun, or maybe not. What is not as nice about this particular example? Yeah, it's not even. We still have to cut it in half. It's not going to be an integer now. But fractions are number two. Numbers two don't discriminate. Yeah. So first of all, we don't want the 1 there. And this is another problem that is not factorable. Graphing, I don't know. We'll find out. But it is not factorable. Let's move the 1 over. We have to figure out what number we're going to add to both sides. So remember, what we do is we take the b value, cut it in half, and you're going to square that. This time, 5 does not nicely get cut in half. Leave it as a fraction. Decimal is okay too, but we're going to prefer fractions. When we square 5 halves, just square the numerator and the denominator. So it becomes 25 fourths. We don't like decimals because sometimes decimals get long. I want exact answers. I don't want rounded answers. And sometimes decimals can get long if you try to keep them exact. Fractions are a neater type of number to work with. Five halves squared is 25 fourths. So the left side, now that I figured out what goes in the C position, what is it that goes inside the parentheses? This is not as obvious of one, but hopefully we remember. Let me go back to our warm-up. I know I got to scroll a little ways. But remember, there was a rule about that. The number that went in the factor was always half of b. It's the number before we squared. So what did we get when we cut 5 in half? 5 halves. And when it was positive. So that's what I'll put in the parentheses. On the right side, 1 plus 25 fourths. Can I simplify that into one thing? Yes, but I need a common denominator. Instead of 1, we think of it as 4 fourths. 4 fourths plus 25 fourths, add the numerators, we get 29 fourths. So now we're ready to square root it. Square root, don't forget, plus minus. Soon we will be talking about quadratic formula, which you've probably used before. Some of you on a problem like this would just prefer to use the quadratic formula, and that's okay. Personally, I would prefer completing the square here, but that's just me. On the right side, when I have square root of 29 over 4, we're not allowed to leave square roots in the denominator, and we want to break the top and the bottom apart from each other. Kind of two problems. So in the top, I have square root of 29. Does the square root of 29 simplify? No. In the bottom, I have square root of 4. Does the square root of 4 simplify? Yes, just a regular 2 without a square root. That's good news because I'm not allowed to have square roots in the denominator. And it's also good news because I'm about to subtract 5 halves, and now I'll have a common denominator. So subtract 5 halves. X equals, I've got a negative 5 halves plus minus the square root of 29 over 2. I could leave the answer like that, and that's acceptable. But because they're both fractions with a common denominator, it's more common that we would write it as one fraction with the denominator of 2, and the numerator would just read then negative 5 plus minus the square root of 29. So if you've done the quadratic formula before, you might have learned it to a song, and we'll do that in the next section. You would get to that answer, and we'll talk about that as another option, but for today, we're just completing the square. I want to do one more. This is my least favorite type of problem to use completing the square for. By the way, that last one, looking at the answer for the last one, the answer was not imaginary. It wasn't nice, but it wasn't imaginary. So if we would have graphed it, we would have got answers. They would have been in decimal form and they would have been rounded. I like these answers better because it's exact. But it would have had 2 solutions on a graph. Okay, number 6. Why do you suppose I'm not particularly fond of number 6? Because of the leading coefficients. So what are we going to do? Well, I'm going to turn this into a problem that no longer has a leading coefficient. What can I do to get rid of the leading coefficient? I can divide by 3, and since it's an equation, I can do that. But I have to divide every term by 3. Oh, good. Now it doesn't have a leading coefficient. It's all good now, right? Well, now our b, not only is it odd or not even, it's a fraction. So that's less exciting maybe than the last problem, but it still works. We can still do the process of completing the square. So first of all, I'm going to move the 1/3. I'm going to add 1/3 to both sides to make space for the c value. So to get the c value, take the b value, and we normally cut it in half or divide by 2, but since that's a fraction, I would rather think of it as times 1/2. Divided by 2 is the same as 1/2, but I don't want a complex fraction, so I'm going to write it this way. But I have a 2 in the numerator and a 2 in the denominator. I can actually cancel those out. So now I have negative 1 over 3 squared. Negative 1/3 squared is positive 1/9. That's what I add to both sides. Remember what number we just squared? We just squared negative 1/3. Negative 1/3 is the number that's going into the factor, x minus 1/3. This adds a little extra rigor. 1/3 plus 1/9, I need a common denominator. The least common denominator is a 9. So instead of 1/3, I will replace it with 3/9. I had to multiply the top and bottom by 3, so 3/9 plus 1/9 is 4/9. Good news. Both the numerator and denominator are perfect squares. That's a good thing for my next step. I like that it ended up being perfect squares in that fraction. So I completed the square, now solve. Square root plus minus. So x minus 1/3 equals plus or minus square root of 4/9. Well, the square root of 4 is 2, and the square root of 9 is 3. There's no square root left over there. So plus or minus 2/3. And to finish it off, add your 1/3. So 1/3 plus, so common denominator, I'm going to write it as one big fraction with the denominator 3. The numerator would be 1 plus or minus 2. There is something I can simplify, so I cannot leave my answer in this form. Go ahead and give both of the answers. 1 plus 2 would be 3. 3 over 3 is 1. 1 minus 2 would be negative 1, so I would get negative 1/3. Those answers worked out nicely. Guess what that tells me about the problem? It was actually factorable. Factoring might have been a better way to do that problem, but it worked. All right, that concludes the notes for today.